if I can, you know what I mean? Okay.
Okay.
Lindsey.
I also had epibatidine.
Yep.
Ooh, good design.
Mine is a little bit different than Naya's and Beth's. They both kind of started with making this kind of like ring with the nitrogen in it, but mine actually starts with the addition of this benzene with the nitrogen and the chlorine on it, just like something that I noticed. But the first step of the reaction is an enol formation. And so what happens is this nitrogen attacks the hydrogen, it goes there, the pi electrons from the oxygen go up, and then when the pi electrons go back down, the pi bond then puts two lone pairs, a pair of lone pairs, a lone pair on this carbon to make a carbanion. And then before the enolate attacks this molecule right here at the carbocation has to form. And so what happens is the pi electrons go up onto this electron here in resonance, and then there's the carbocation. And then the enolate attacks the carbocation, and it forms a tetrahedral intermediate, and then the pi electrons re-aromatize, and the iodine and the remaining rest of the molecule is kicked off to form this molecule right here. And like we talked about the enol formation in Orgo 2.
So can you go back one step, Lindsey, just because I want people to just sort of notice how weird of a reagent this is. That
yeah, it's really weird.
If you even just look in the box, right,
Yeah,
that it's two aromatic rings attached to a single iodine, which makes the iodine positively charged. And that somehow induces the carbon that's bonded to the iodine to be susceptible to attack by nucleophiles such as enolates. I'd never seen this before. It's very weird. I don't even know how you would make a dye substituted iodine compound, actually. I don't know how you would do that. But anyway, very surprising sort of way. And like she said, here in the first step, they're putting that nitrogen containing aromatic ring on. So it's kind of interesting.
So they like form the enolate and then do the next one.
Yep.
I also forgot to talk about how it's a, it's a, why does it keep doing that? It forms an enantiomer. So it's like kind of what we talked about in, with DJ about how like it has an enantiomer and then you have to do like diastereomers with it. But it's 94% E.
Yeah, that's crazy.
Yeah, which is like pretty high, I think.
Yes, it is.
And then the second step is just a reduction with sodium borohydride, which we learned about in Orgo 2, and I think we might have talked about it a little bit in Orgo 1. And what happens is the pi bonds from the electrons go and attack the hydrogen, and the boron attacks what would be a carbocation. And then another cyclohexanone comes, and the same thing happens, and then that happens 4 times. So then the boron has 4 oxygens attached to it, and then in the acidic workup, sorry, I don't know why that keeps happening. Then they're all protonated and it becomes an alcohol group. And then the step 3 is like made of 2 parts. The first part is just making the mesylate group, which we kind of talked about like today and in the past, how it's like similar to a tosylate group. And so the alcohol group then forms to a mesylate group, and then the mesylate group works as a leaving group in next reactions.
Good.
And so what happens is the oxygens just attacks the sulfur, the chlorine pops off. Chlorine, then there's a oxyanion, and the chlorine anion attacks the hydrogen and forms HCl, and then we're left with this. And then the second part of the reaction with the CF3CO2H is just a deprotectant of the Bach group on the nitrogen, which Beth kind of touched on, how CF3 CO2H is, you can see like in the structure, like there's a carbonic acid, and so it's like kind of acidic, and then the fluorines make it more acidic. And so what happens is the tert butyl group is a stable cation, so it kind of just like falls off in acid, and then you can see that this is kind of left, it looks like carbon dioxide, and the carbon dioxide just pops off, and then we're left, and then it gets protonated, and we're left with NH2. And then the last step is very weird. Very interesting. So the NH2 actually attacks the carbon right here. It's an intramolecular SN2 reaction, which we talked about in Orgo 1. And the nitrogen attacks the carbon, and it forms this kind of bridge right here in this carbanion, and then the mesylate group just pops off, and then you're left with the bridge, and then you have epibatidine.
That would be one step, of course. Do you see that? Like the mesylate would leave simultaneously with the nitrogen leaning over to make that new bond. Do you see what I'm talking about?
Yeah.
Because because you have the SN2 as like two steps, but it's one step.
Yeah. Okay.
Yeah, but that's very weird, right? It's like absolutely different than everybody else's to in the construction of the bicyclic ring to use this intramolecular SN2 reaction with nitrogen. I think was very surprising and a little risky, actually, right?
Mm-hmm.
I don't know if you had the thing what their yield was for this one, but
I can look at it. Yeah, we have it. They're actually all pretty high yield, so it's 83, 90. This is the formation of this right here is the only one that's low with 41%. But
yeah, they don't have one for the last step though, which is interesting.
No.
Yeah. Great.
Cool.
The other thing I wanted to point out, which is a little surprising, is that the base up here, I think, has sort of come up a lot for people. Do you see again that it's a nitrogen anion, right? That's paired with lithium that made the enolate. I think we've seen those kinds of compounds quite a bit used as strong bases to deprotonate things. Do you kind of see what I'm talking about? And this one, like Lindsey said, this reaction is enantioselective, and part of that is because the base is chiral. So the base, at least in principle, can now I don't quite understand this actually, but the base can remove a proton enantioselectively. Now, I don't know how that would be maintained because it would be delocalized and flattened out, but regardless, they used a chiral base to impose some enantioselectivity onto the alkylated product, which is, I guess, also kind of interesting and a little bit unusual.
Yeah.
Thank you, Lindsey. That was nice, everybody.